All right, everyone, buckle up because today we're diving into a story that literally rewrites the early chapters of mammalian history. You know how we always think about mammals giving live birth, right? Well, it turns out that monumental shift might have happened way earlier than anyone ever imagined. We're talking 90 million years earlier. It's wild.
Yeah, Chloe, it really is a mind-blower. For so long, the consensus was that viviparity, live birth, really took hold with the theory in mammals, which emerged around 160 million years ago. But this new research, looking at a creature called Chinquodon theotonicus from about 236 million years ago, just flips that whole timeline on its head. It suggests our ancestors were doing the live birth thing in the Triassic period.
Chinquodon theotonicus! What a name! And for those unfamiliar, we're talking about cynodonts here. These weren't exactly mammals as we know them today, but they were incredibly close, our direct ancestors. Imagine dog-toothed creatures that basically paved the way for all of us furry, warm-blooded beings running around now. And to think they might have been giving live birth back then, it's just incredible to picture.
It's not just incredible to picture, Marcus. It's incredible how they figured this out. It's not like they found a pregnant Chinquodon fossil, right? The researchers, led by Leandro Gaetano, looked at growth rings within the fossil bones of an adult Chinquodon. They identified something called a neonatal line, essentially a microscopic dark ring that marks the intense metabolic stress of being born. It separates prenatal tissue from postnatal tissue. It's like a biological birth certificate etched in bone. A biological birth certificate! I love that, Maya. And here's where it gets even cooler. By analyzing these growth rings, they could estimate the size of the animal at birth versus its adult size. This particular Chinquodon was about 1.7 kilograms at birth and around 12 kilograms when it died. That's a newborn to adult body mass ratio of about 14%, and that apparently is the key.
Exactly, because when they plotted that ratio against thousands of modern creatures, everything from reptiles like turtles and crocodiles, to birds, to different types of mammals like egg-laying monotremes, pouch-rearing marsupials, and placental mammals like us humans, Chinquodon grouped with modern placental mammals. Its ratio was almost identical to a small African antelope called the bay duiker. That's a powerful comparison.
So basically, the baby Chinquodon was pretty hefty, relatively speaking, just like a modern human or an antelope baby, which is a hallmark of live birth. Whereas if you look at monotremes or marsupials, or definitely reptiles and birds, their newborn to adult ratios are much smaller, sometimes as low as 0.15%. Imagine a kangaroo joey right after birth. It's tiny compared to its mother. This Chinquodon baby was already a solid chunk of its adult self.
It makes perfect sense when you lay it out like that. The implication is huge, but it also makes me wonder, what enabled these cynodonts to even consider live birth? What was it about their biology that might have made this evolutionary leap possible so early? That's a great question, Maya, and the article actually touches on it. Cynodonts were already pretty advanced compared to their ancestors, the therapsids. They had differentiated teeth, incisors, canines, molars, allowing them to process a wide variety of foods, cutting, tearing, grinding. Their jaws were also adapted for chewing, and crucially, they developed a secondary palate that allowed them to chew and breathe at the same time.
Chewing and breathing at the same time. That sounds so fundamental, yet I bet it was a game changer back then. I mean, we take it for granted now, but imagine having to stop breathing just to eat. That would seriously slow down your metabolism, right?
Exactly, Chloe. Speeding up digestion and enabling a higher metabolic rate was massive. It means cynodonts were at least partially warm-blooded, and that, along with their burrowing abilities, is thought to have helped them survive the biggest mass extinction event in Earth's history, the Permian extinction, around 252 million years ago. So they were already a resilient, highly adapted group.
So a higher metabolic rate, differentiated teeth, efficient chewing, all these advanced features could have created the perfect storm for viviparity to become advantageous. If you can fuel a larger, faster-growing baby internally, rather than relying on an external egg, that could be a huge survival advantage, especially in a changing environment after a mass extinction. It's like all the pieces were falling into place for them to eventually become true mammals. And if they were doing live birth back then, it throws up some really interesting questions. Like, did live birth evolve once, super early on, and we just didn't realize it? Or did it evolve multiple times in different lineages?
That's precisely what paleontologist Randall Ermis, who wasn't involved in this specific study, pointed out. He says it opens up the question of whether it evolved once, much earlier, or if it evolved at least twice. And that's the kind of big evolutionary mystery that keeps paleontologists up at night. The challenge now is finding more fossil evidence to test these hypotheses.
And finding that evidence is incredibly tough, isn't it? We're talking about incredibly delicate embryonic tissues that fossilize even less frequently than adult bones. So while this Chiniquodon study provides a compelling argument, it's not the final word, and other experts are rightly cautious.
Indeed, because there's actually strong evidence that other early mammal ancestors and relatives were still laying eggs even after Chiniquodon. Take Lystrosaurus, for example, another dicynodont that survived the Permian extinction. Scientists found a tightly curled Lystrosaurus embryo preserved inside a shell, clear as day, egg layer. Oh, so not everyone was on the viviparous train then. That's a good point that complicates the evolved once theory. What about later cynodonts?
Yeah, and then there's Chiantotherium wellesi, a cynodont that lived around 166 million years ago. Fossils of this creature found in Arizona show an adult with 38 individual young. That number, 38, is much more suggestive of a large clutch of eggs, like a reptile or bird, than a small litter of live-born babies, which is typical for mammals.
So you have these examples, Lystrosaurus and Chiantotherium, that indicate egg-laying was still very much a thing, even in cynodonts that lived later than Chiniquodon. It highlights why paleontologists like Eva Hoffman from the American Museum of Natural History, who studies cynodont evolution, are pretty conservative. She's quoted saying it would require strong evidence to demonstrate viviparity, and she hasn't seen that for any non-Therian cynodont yet. It just means the debate is very much alive. Which is why this Chiniquodon discovery is so pivotal. Even if it's not the definitive case-closed answer, it introduces a completely new data point that challenges our long-held assumptions. It forces us to reconsider the entire timeline and the branching paths of evolution. It reminds us that science is an ongoing conversation, not a series of static facts.
Absolutely. It's not about being right or wrong, it's about continually refining our understanding based on new evidence. And this Chiniquodon fossil, with its tiny yet chunky newborn bones, is certainly strong new evidence pushing that timeline way, way back. It makes you wonder what else is out there, waiting to be discovered, that could fundamentally change how we see our own evolutionary journey.
It truly is. Every new fossil is a puzzle piece, and sometimes a single piece can shift the entire picture. This study has certainly done that for the evolution of live birth. It's a testament to how much we still have to learn about the deep past and the incredible adaptations that led to the diversity of life we see today.
And the fact that these ancient ancestors, these cynodonts, were so robust and adaptable that they not only survived a mass extinction, but potentially evolved such a complex reproductive strategy so early, it really puts their evolutionary success into perspective. They weren't just stepping stones, they were innovators. Innovators indeed, and it just makes me even more excited for the next batch of discoveries. We'll definitely be keeping an eye on this space. Maybe one day we'll find that fossilized embryonic tissue that Eva Hoffman is looking for, and it will confirm or deny this theory once and for all. Or maybe it will just open up even more questions.
Exactly! The beauty of science. So whether you're a proud placental mammal, a fascinating marsupial, or even a super cool egg-laying monotreme, remember that your distant ancestors were probably doing something pretty groundbreaking way back when. Thanks for joining us on this prehistoric journey into live birth. We'll catch you next time.